Hi, I'm Jamie Milliken, and this is Lab 4 of Physics 2, Circuits and Capacitors. We will have an introduction and go over the first simulation, then the second simulation, and then go over the results and conclusion. So first, this lab was conducted with PHYS simulations to show the principles of energy conservation and current conservation. Several circuits were observed to predict the behavior of resistors and capacitors and measure the conventional currents as well as potential differences. Some of the principles we will use are energy conservation, specifically the loop rule, which says the change of potential of the entire circuit will be zero. The conservation of charge, we will use the node rule, so the current in is going to be equal to the current out. The potential difference across a capacitor is equal to Q over C, and potential difference across a resistor is equal to I times R. Assumptions and results. So we're going to assume the wire resistance is negligible as well as resistance along the ammeter, and the system is defined as a circuit for every simulation and surrounding is everything else. So the first simulation will go over charge conservation and energy conservation in a series circuit. So with the prediction, the current in is equal to the current out. So here we have the total R is equal to 147 ohms. So the current would be 0.02 amps. And we found that is true across the entire circuit with these two screenshots. And if the ammeter is flipped, we would expect the same current will flow through, but the opposite sign will read on the ammeter. For the second part of this experiment, we're going to split up the circuit and watch the change of potential, which we would expect to be -3 volts across this broken circuit because the change in voltage through the battery is going to be 1.5 plus 1.5 volts. And we know that the delta V round trip is equal to 0. Here I show the results of the simulation across of the change of potential across A to B, B to C, C to D, and etc. So you'll notice that the delta V across all the sections must add up to 0 anyway, and it does when we do this experimentally. And the graph on the bottom shows those changes over the whole circuit. To confirm the predictions were true, we're going to calculate a couple values, just the resistance of each of the portions of the circuit. So for the 47 ohms resistor, we have delta V over I is equal to 0.96 over 0.02, which is 47 ohms. We have the same confirmation for the 100 ohms resistor, 2.04 over 0.02, and for the wire in the ammeter, we find that the resistance is 0. Next, we'll get into the RC circuit, and I've written down some of the observations when we did certain things to this circuit on the simulator. So first we used the 10 ohms bulb, which had the same results overall for the first 4 categories. When we connected it to the battery, the light would start up bright and end with no light. So the current is decreasing until it gets to 0, and that is the same as when we disconnect the battery and let the capacitor discharge. So the time it takes to charge the capacitor was around 6.2 seconds for the 10 ohms bulb, and we have kind of around the same ballpark to discharge the capacitor for the 10 ohms bulb, but for the 20 ohms bulb, we have a longer time to charge and discharge the capacitor. So on this slide, I'm going over the results of watching the change in potential over time for a discharging capacitor. When we model this with a logarithmic relationship, we'll find a linear pattern with the curve -1 over RC, which is exactly what we would expect with the principles of physics in this concept. So let's get into the what ifs. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What is different about the real ammeter, and how would it affect the circuits we hooked it up to? An ammeter in real life would have some resistance and therefore would skew the results, showing more resistance overall. Next, if we were doing this lab in real life again and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would the ideal model predict the capacitor to reach full charge? So we would expect the capacitor to charge more slowly in real life because the wire has some resistance that we don't account for in the ideal model. To conclude, using some ideal assumptions that would not be supported if the experiment was conducted by hand, the PhET simulations confirmed that the principles of the circuits we learned in class hold true. The results are, as such, ideal and would not be good for practical use, but can be a good approximation.